Hi, good day, everyone. I'm glad to see you on the first talk of the Hydra 2022, and I'm glad to announce our first speaker, Raphael Carvalho. And today, Raphael Carvalho is going to tell us about various compaction policies of the LSM-tree. Raphael works at ScyllaDB, modern and fast NoSQL database, compatible with both Amazon DynamoDB and Apache Cassandra. Raphael started working at ScyllaDB at 2015, while ScyllaDB itself exists since 2014. So I believe Raphael is one of the oldest contributors of ScyllaDB, and he definitely knows a lot about ScyllaDB internals, and today he's going to share his knowledge with us. ScyllaDB uses LSM-tree as its storage engine, and one of the most important things that you should think about when designing LSM-tree-based storage engine is its compaction policy. Raphael is going to outline pros and cons of different compaction policies and explain what makes compaction policies implemented in the ScyllaDB so efficient. So good day, Raphael. How do you feel?
Hi, everyone. Thanks for having me. I'm really glad to be here. And as Eli already said, today I'm going to talk about how ScyllaDB makes LSM-tree state-of-art, LSM-tree compaction state-of-art by leveraging how we can use the run conjecture and controller theory in the industrial controller to make sure that compaction is as good as possible. So let me get started.
Sorry. I want to remind you that you may ask questions during the talk, and that after the talk is finished, you may assess it in your player, and that after the talk we'll have it as discussion. So I think we may start.
Okay. So I have been working on ScyllaDB since its early days. Actually, before ScyllaDB, the company was working on the operating system OSV, which is a unikernel designed completely for the cloud. But then we later found out that we would like to work on distributed database because in OSV we found inefficiency in Cassandra, and then we decided to implement a Cassandra like database from scratch, with the API being compatible and also reusing the storage format. That's why we use the LSM-tree, and the storage format is the SSTable like Cassandra. Okay, so I think that's all I have to say about myself. Let's move on to the interesting part. Okay, so the agenda for today, I'm going to explain what LSM-tree compaction is, the compaction strategy and policies. I'm going to use the term strategy and policy interchangeably. It's basically the algorithm that decides which files to compact together, when to compact those files, the data layout, and so on. I'm going to talk about the trade-offs on the amplification factors, because there is no perfect compaction strategy. We have to find the best one for your particular workload. The famous incremental compaction, the hybrid policy incremental compaction, which is going to be good for overwrite-intensive workloads, and self-tuning compaction. It's basically to save the DBA from being stuck in an endless tuning cycle. So I'm going to talk more about that later. Okay, so before I go into the deep topics, I'm going to explain quickly what LSM-tree compaction is. I already said that the storage format is SSTable. Those are the files that are created over time. So the updates to the database are inserted into a memory table, a table that sits in memory. The updates are also written into the commit log for durability. And this memory table is sorted according to a token, which is like a hashed value derived from the partition key. Okay, so this is how it works. When the memory table fills up with the updates, this memory table is is flushed into a sorted file sitting on disk. This file is sorted because the memory table is sorted. I'm going to explain why the actual reason behind making this memory table and SS table sorted is that we want to make it easy to search a key inside the memory table, and also to allow the merge, which is essentially the compaction process. So by keeping out SSTable files sorted, we allow the compaction to be easy, so we can make it efficient. So the random writes written to the database, they are, like I said, they are in the memory components, which is the SSTable, and we allow those random writes to turn into the sequential writes at the disk-based component, which is the SSTable, and that's how LSM-tree write path allows for very efficient writes. So this is what happens after a while. We have many separate SSTables because we never modify our existing file. Those files are immutable. So you can think that over time, different SSTables may contain redundant data, the old and new values of the same cell. So it could happen that different rows in the same partition, you have those partitions spread across multiple SSTable files, which increase the read amplification. And it wastes disk space because it could happen that we are storing redundant information, slowing down the reads, because when data is split across many SSTable files, the read requests are going to read from more SSTables. And I think I would like to say that the way most of LSM-tree implementations mitigate this problem by using Bloom filter and also keeping metadata in memory to allow files to be quickly filtered, because it could happen that some files doesn't have a given set of keys. So we allow, if we're reading a particular key, we can only try to open the files that store this key, allowing the read performance to be better. So the process of compaction is when those files accumulated, we are reading them, and we are compacting the data in those input files, and we are going to output a file containing only the most recent information without having redundant data. And merging those input files is an efficient process because, like I said, the files, the SSTable files, they are sorted. So we can apply the K-way merge algorithm to make sure that the compaction process is efficient. We have like an iterator in each input file. When we are done compacting the current partition, we can then proceed to the next one. So this is why we keep the SSTable files sorted to make the compaction process very efficient. So it will happen that if we don't, if the workload is write only, meaning that we don't overwrite data, we are going, when compacting those two input files, we are going to output a larger file containing the data, the merged data of those two input files. So when we are done compacting, we are going to replace the input file by the output one, the input files, and by the end of compaction, we are going to release the disk space. One of the problems without incremental compaction is that we are only able to release the disk space of the input files after we are done writing the output file. And like I said, that only happens without the incremental compaction approach. Okay, so this technique of keeping the sorted files was the first mention I know was in a paper in 1996. Then its first known usage was in 1999, because as the data volume was increasing, meaning that the database should keep up with the write rates. B-tree wasn't as efficient, and we needed something that allowed to convert those random writes into sequential writes to make sure that the write performance is good to accommodate the write load. So I already talked about many properties of compaction efficiency that we allow for contiguous I/O and for read and write, because we continuously merge the data from the input files. We don't have to like perform a random read because the files are sorted. We are able to break the whole compaction operation into smaller pieces, and by employing internal schedulers, we are able to remove the impacts on latency. I'm going to talk about the schedulers, the internal schedulers available in ScyllaDB later, which is made available by the C# framework. And I also would like to say that we apply the industrial controller theory to make sure that compaction doesn't use more resources than needed, doesn't use more CPU and disk to clear the compaction backlogs. Because if compaction is aggressive, it would happen that compaction steals resources from the foreground requests. So now, given that I already explained what compaction is, now the question is when to compact and which files to compact. I already said that I'm going to use the terms policy and strategy interchangeably. So this is the compaction strategy. It's a pluggable property of the database, so each table can have like its own compaction strategy, because different tables may have different workload. One could be write intensive, where other could be like more read intensive. So the right compaction strategy, which is when and which files to compact, it depends completely on your use case. So there is no like a global universal compaction strategy, which is good for everybody. That doesn't exist. So the compaction strategy is basically about reshaping the LSM-tree, because like I already saw, the files accumulate over time. So we needed to know which files to compact and when to compact. That's according to the algorithm. The algorithm depends on the compaction strategy used. And this shape defined by the compaction strategy has like an influence on the application factors. So we are going to look at the good and bad properties of each compaction strategy. So it could happen that like a policy is going to have higher read amplification, higher space amplification, but lower write amplification, which is about how many bytes I need to compact for the compaction strategy to be satisfied, which means there is nothing to compact. So I think it's very important when we talk about amplification factors in the compaction world, we wanted to talk about the run conjecture, because to understand the trade-offs between the compaction strategy, we needed to understand what run conjecture is. It's like the cap theorem for distributed database that say a database can't be good at everything. It has to make some choices about availability, partition tolerance, and so on. So in the compaction world, it's the same thing. A compaction policy has to make choices, has to make trade-offs, has to decide on whether the policy is going to be better for writes or for read and space. So the run conjecture basically states that a storage system can't be optimal in read, update, and space. So it's impossible to decrease all the amplification factors at once. You have to make choices. You can optimize for write, but you are going to have to sacrifice read and space. And the other way around, you can optimize space and read, but introduce a new problem, which is write amplification. So this is more or less how it looks. You have like the leveled policy, which is good for read and space, but it sucks at the write amplification, and also the other way around. This is the three-dimensional efficiency space, which represents the trade-offs. A policy cannot be optimal at all factors at the same time. So now I'm going to talk about, it's going to be a brief history of the compaction policies in Cassandra and ScyllaDB. If we look at the timeline, the original LSM paper presented the leveled policy first, then the tiered policy arrived later with the big data, with the big table paper to mitigate the write amplification. In Cassandra and ScyllaDB, it was the other way around. We started with the tiered policy, which is efficient for write performance, but it's not good at the read performance because it has like a substantial waste of disk space, because the redundant data can accumulate more easily with the tiered layout in the LSM-tree. When we think of compaction strategies, we have to think that compaction strategy is trying to set the shape of LSM-tree, and the shape has a direct influence on the application factors. So I say that level strategy, it fixes the space and read, but introduces a new problem, which is write amplification. So I'm going to introduce here the policy. You can see how it works under the hood. So it's like the Cassandra oldest compaction strategy, like I already said. It dates back to the big table paper. So it has several compelling properties, which made it popular as the first and default compaction strategy. But it was clear that we also needed a leveled policy which reduced the writing space amplification. So this is how it looks like, the LSM-tree shape when tiered policy, when tiered compaction strategy is used. So when we have like enough SSTable files because like I said, the database writes to the mem table, and then the mem table has to be flushed into the SSTable file. Those files accumulate over time. So when those files accumulate, we are going to wait for like in ScyllaDB and Cassandra, the threshold is 4 by default, meaning that when 4 similar sized files accumulate, we are going to compact them together. So the output, if you are not like, if the workload is not overwrite intensive, the output is going to be like the combination of the data from the input files. And we are going to place the output into the next tier, because the tier only has similar size of files. So the tiered algorithm is going to place similar sized files into buckets. And when a bucket has accumulated 4 files by default, we are going to compact these buckets together. And that's exactly how the tiered policy works. We wait for accumulation in a given bucket, and we compact the input data into the output, and we remove the input data after the compaction process completed. So the amplification factor, the write amplification for tiered policy is log n. That's because we are the amount of tiers that a given byte will have to travel through is a logarithm of the total data size. So we could only have like a small amount of tier, which is like like a small amount of tiers. It's a log. That's why we say log n, because you take the amount of the data size, you divide it by like the size of the SSTable in the level 0, which is where recently flushed SSTable sits, and then we can calculate the amount of tiers, how many tiers the LSM-tree layout is going to have. So given that most data is in the highest tier, we can say that the data only has to pass through a couple of tiers. The read amplification is not so good, because if your workload is overwrite intensive, it could happen that if you keep updating the same partition, it could happen that a given partition would be spread across all the SSTable files, because if you keep updating a given partition, then different SSTables is going to have that partition. So when reading that partition, you're going to consider all the SSTable. But we have the in-memory Bloom filter, which allows filtering out the SSTable, the relevant SSTables. But for large partitions, that doesn't help, because the Bloom filter only helps if you have like a single row partition. But if your partition is composed of millions of rows, then it could happen that those million of rows is spread across all the SSTable files, affecting the read amplification and space amplification as well. So here I explained the space amplification. We have to think that space amplification is going to be perfect if everything is in a single SSTable file. And this weakness in the tiered policy is what made people introduce a leveled policy in Cassandra. So there is a saying that storage space is often the primary bottleneck when using flash SSDs in particular workloads. So there is a need to have a strategy to have a compaction policy which is going to reduce the space amplification. So that's the space amplification for tiered policy. If we wait for many files, then it could happen that a bucket contains all the files in a given bucket to contain redundant information of a given partition. It could happen that a given bucket, all the SSTables in a given bucket contain redundant information. Now we level the policy. It was introduced later in Cassandra 1.0. It's based on Google's LevelDB, which itself is based on Google Bigtable. The basic idea behind the leveled policy is that we are no longer going to have those huge files, those files of exponentially large, because in tiered policy we have those tiers, those buckets of exponentially larger sizes. For example, the next tier is exponentially bigger than the tier below, and so on. So the basic idea behind the leveled policy is to break those files into a layout into fixed sized fragments. Basically, we are going we are only going to have like one file, like one run of files in a given level. We can think of a level like a tier, but we use the term level because the scope is leveled compaction. So each level in the LSM-tree layout, data layout, is going to have like a run, which is a sequence of disjoint files, meaning that in level 1, we are going to have 10 files. In the level 2, we are going to have 100 files, and in level 2, 1,000 files. And when I say disjoint, I'm basically saying that those files in a given level do not overlap in the key range, meaning that if I want to read a partition, read a key, I only have to look at one file for each level. So by allowing by having this layout, we also reduce the space requirement for compaction to happen, because given that we can only compact a subset, because we know in tiered policy that we compact the entire bucket together. But with leveled policy, we are only going to compact a subset of the level. So if level 1 has 10 files, I can only compact one file from level 1 to level 2, which allows the space requirement for compaction to be reduced to a limit, where the limit would be the amount of files of fragments being compacted together multiplied by the amount of files. It's because all the fragments in leveled policy is fixed in size. We use 106 megabytes by default. So that's how it looks like. So we can see that when we want to compact, when we have enough files in level 0, I think it's worth mentioning that level 0 acts more like the tiered policy, because it's like a staging level where we can allow the files to accumulate before compacting level 0 into level 1, and that's what reduces the write amplification. So the output is placed into level 1. We get one file from level 0 and merge it into the next level, which is level 1. And so we place the output into level 1 itself. So it could happen that level 1 exceeded its capacity, because each level has its capacity on the amount of fragments. We call a fragment a SSTable, because it's like a file broken into a fixed size chunk. So when we wanted to promote a file from level 1 to level 2, because level 1 has exceeded its capacity, we are going to compact the file in level 1 with other overlapping files in level 2. And given that level policy uses a 10 out of 10, meaning that's essentially the size ratio between the levels. So you can see that level 2 is 10 times larger than level 1, and level 1 should be 10 times larger than level 0. That's the goal, the layout goal. So given that each level is exponentially larger than the level before, we can say that each fragment, a fragment on level 2 is 10 times bigger than a fragment on level 1. So on average, it could, when promoting a file from level 1 to level 2, we are going to find the 10 overlapping files in level 2. So the output is placed into level 2 itself, and so on. So if level 2 has exceeded its capacity, then we are going to do the same by picking a file from level 2 into level 3. So this is the space amplification for level compaction. Because of the SSTable counts, because we use the 10 out of 10, meaning that 90% of the data is going to be on the biggest level. That's because we use the 10 out of 10. So if we have like 1 terabyte of data, 1 terabyte of data in the LSM-tree, about 900 gigabytes would be in the highest level, 90 gigabytes in the second biggest level, and so on. And if you do some math, you're going to see that we achieve with this goal, we achieve a space of amplification of 1.1, because the smaller levels, the levels other than the biggest one, can only have 10% of can only waste 10% of space. Given that each promotion from one level to the other is going to find an average 10 to 12 overlapping files, each compaction only needs a temporary space of we came up with the worst case of 12, because it could happen that we find some overlapping files on the edge. And given that the fragment size is 160 megabytes, we can come up with an estimation on the amount of disk space that the compaction level policy is going to take. So that's how level policy achieves the space amplification of 1.1. The read amplification, that's the amount of SSTable files. It's not as good as in tiered policy, but we have to remember that given that a given level in level policy have the set of files in a given level have disjoint key ranges, where the ranges itself are cached in memory, we are able to quickly, efficiently filter out the files that do not overlap with the key we are trying to read. So we are when trying to read a particular key, there could be like only one file in each level that has the key, because each level has only disjoint files which do not overlap the key range. So under some assumptions, we could say that 90% of the reads is going to just need to read one SSTable. The reasoning is that 90% of the data is in the highest level, and only 10% of the space is wasted. But it could also happen that that's only under some assumptions. For the worst case, it could happen that when updating a large partitions, all levels is going to have like a row for the partition. So we are actually going to read from all the levels, but the amount of levels is also small because we use the fan out of 10. So the fan out of 10 is good for the read and space amplification. So level compaction is not the best invention since sliced bread, because it has the problem of write amplification. Because to achieve this layout, you can think that we have to write a lot. So, but all the estimations for the write amplification are the worst case. So that's like the theory, but it doesn't necessarily happen in practice. I can give a good example, which is high time locality workload, which is basically a data recently written has a high probability of being modified soon. So that's high time locality. And for this workload, the data being updated is going to sit on the smaller levels, which allows the write amplification to be reduced. But for the worst case, if you have enough write load, then LCS leveled policy could not keep up with the write rate, so the read and space advantages would be lost. So when trying to use level, you need to see if the write amplification it causes won't make it a problem for you in terms of write amplification. So write amplification problem makes leveled policy a bad property, a bad policy for many workloads where the amount of writes are not negligible. So this is write only. It's a benchmark which compares leveled versus tiered policy. So the tiered policy at some point needs, as we know, we have to wait for the output file before we can reuse the input files. And that doesn't happen in leveled policy, as we already explained, because we can only compact a subset of the levels. So the space amplification with level size tiered with tiered policy is terrible, because if we are compacting like 1 terabyte of data, then the space requirement is going to be if there is no duplication, if there is no ways of if there is no space amplification, then the worst case would be the amount of space needed for tiered compaction would be the size of the input data, because the output could be as large as the input size, and that doesn't happen with leveled policy, which is more or less the concept we apply for incremental compaction. So the write amplification, we leveled policy in this particular workload wrote a bit more than twice the tiered policy. Okay, so we need to remember that the leveled policy, the right amplification for leveled policy is not only a problem if you have like 10% right, because the right amplification could be so high that we amplify that 10% into a much larger amount. So 10% right could be not negligible. So it could be a lot, and the node could not keep up with the right rate, even though you thought that 10% right would be small, but in reality, it could be huge. So compaction, if the node can't keep up with the right rate, the compaction work would pile up, meaning that the compaction backlog would increase. Then we would have problem with the space amplification and the read amplification, and the benefits of leveled policy is lost because it could happen that your workload has a non-negligible amount of writes, even though you thought that most of the operations in the database would be read, but the amount of writes amplified so much that it started bringing issues for your node. So compaction backlog would increase, and the problems would start happening. The read latency would increase, and so the LSA could be broken. Okay, so the overwrite workload would be like the worst case for tiered policy, but a good workload for leveled policy. So for tiered policy, it could happen that if you keep updating, overwriting the same data over and over again, that partition could be stored across all the files, because as you flush the mem table into the SSTable file, then we would start accumulating the redundant version of the partition that's being constantly updated. So overwrite intensive workloads would be like the worst case scenario for tiered policy. So you may consider switching to leveled policy, but then we introduced the hybrid policy, which could be like it would be between the tiered policy and the leveled policy in terms of amplification factors. So it could be it's an alternative that could suit better your use case. So this demonstrates that the tiered policy could be really bad at space amplification when we have overwrite intensive workloads. So we have multiple files containing redundant data. The space amplification is huge. So like I said, it's a problem with tiered policy, but it's leveled policy is able to clear the backlogs. So even though the workload is overwrite intensive, it's able to compact the levels in such a way that the amount of redundant information would be considerably reduced. So can we create a new compaction algorithm with the low write amplification, but without the space requirement that affects the tiered policy? Because like I said, space amplification comes into two flavors. The first flavor is the amount of space needed for compaction to complete, which is, like I said, in tiered policy, we have to wait for the input files to the compaction to complete before we can release the disk space of the input files. But we found that's a problem because users of tiered policy has to leave about 50% of free disk space, which is bad because the storage density decreases because you can't use the disk of your nodes up to most of its capacity, storage capacity. So there was a need to introduce incremental compaction approach in ScyllaDB, which is not available in Cassandra yet. So the basic idea is to borrow the idea of runs from the leveled policy, instead of having those huge files in tiered policy, we are going to have runs, but in each level we are going to allow accumulation. So the layout, you can think that the layout with incremental compaction, the LSM-tree layout is going to be the same as in tiered policy. We are going to allow accumulation in each level, in each tier, but each file, you can remember the file in the tiered policy, each file will be broken into fixed size fragments. So when compacting a given bucket, when compacting a given tier, we are going to be able to release the input fragments of those previously huge files in the tiered policy. And we are going to be able to release the input fragment as we create new output fragments. Given this works because the files are sorted. So when we are done writing an output fragment, we can look at the input fragments. We can look at the input fragments that were already compacted, and we can release them. And given that we are going to keep the same LSM-tree data layouts, we preserve the right amplification of the tiered policy and also the space, the read amplification. But with incremental compaction, we are fixing the space overhead that affects the tiered compaction. So as you can see, as we output new fragments, we are able to look at the input fragments and release the ones that were already exhausted by the incremental compaction process. On average, we will release one input fragment for each output fragment. If the workload is overwrite intensive, it could happen that we may need a few more fragments, but still the limit on the space we require. The space requirement is limited. It would be like a f, where f is a factor multiplied by the fragment size by some factor it would be a factor multiplied by the fragment size multiplied by the amount of input SSTable runs. So you can see that the compaction process works exactly as in the tiered policy, but the difference is that each SSTable is broken into fixed size fragments, where each fragment doesn't have, where all the fragments composing an SSTable doesn't have key overlapping, which allows us to not affect the read amplification, because for each SSTable run, we are able to look at only one fragment to satisfy a particular key read. So it was said that we could apply some techniques to allow the incremental compaction policy. Now in ScyllaDB, incremental compaction is a policy itself. So the user could pick incremental compaction policy instead of tiered policy. So incremental compaction policy would be like tiered policy 2.0. And the incremental compaction policy also allowed us to do cross-tier compaction, which means compacting the files, which is basically about mixing the concept of levels and the tier algorithms to have something in between them, allowing the incremental compaction user to use this policy instead of going to the level policy. So incremental compaction policy plus hybrid layout, which is a mix of levels and tiers, we could allow the user to go with incremental compaction for rewrite intensive workload. But that doesn't exclude, that doesn't make level policy obsolete. Instead, it's like a new option for users that want something in between, that doesn't want to suffer with the right amplification of level, but still wants to have a good read and space amplification, not as good as level policy, but good and much better than the space and read amplification that the tiered policy can provide for overwrite intensive workloads. So this is the space amplification. As you can see, the write and the read amplification remains the same as the tiered policy, but what changes is the space amplification. So the space amplification, actually, we are going without the hybrid layout. The space amplification is still gonna be bad for overwrite intensive workloads. But what we are changing with incremental compaction without hybrid layout with tiered because incremental compaction can come into two flavors. The first one is incremental compaction with the tiered policy, and incremental compaction with the hybrid policy. The user can pick which one the user wants. So the incremental compaction, because incremental compaction, it was firstly introduced with the tiered layout only, without the hybrid layout. So when it was first introduced, it only fixed this space requirement for compaction to complete. But then we found the need to introduce this hybrid layout. So the difference is huge, as this benchmark shows. We fix the space requirement, so the spike is not there anymore. You can see that we are able to release the fragments as compaction proceeds with the incremental compaction, which is great because now the storage density of the nodes increase. Okay, is it enough? I ask you the question. Is it enough? Turns out it wasn't, because we wanted to make the incremental compaction good for overwrite intensive workloads to provide the alternative to lambda policy, which is like something in between, as already said. So we can see that the SCCS, which is the tiered policy, and ICS, which is the incremental compaction policy, they are in a similar region in the three-dimensional efficiency space, which represents the run conjecture trade-offs, the run trade-offs. So it's not enough. We can do better, basically by combining the layout of tiered and lambda policy. So we are basically wanting to combine them to bring something new, which is going to be good for overwrite intensive workloads, which is something which is alternative to lambda policy, which may not be good for if the amount of writer is not negligible. So you could go with this incremental plus hybrid if you want. So how does it work under the hood? It's basically all the tiers are going, all the tiers, but the largest one will allow accumulation of the sorted run. So it's the tiers, but the largest one is going to be like in tiered policy. We're going to allow accumulation of files in those buckets. Because you can think of the hybrid layouts like a set of levels, where the biggest level is going to work like a level. I have a diagram which makes it clear. So you can see that the tier 0 is going to be write optimized, the tier 1 is going to be write optimized, and the largest tier is going to behave like a level in the lambda policy. So we are basically mixing the concepts, and it's good to keep the smallest tiers write optimized, because that's where new data is going to be flushed at. So if it happens that the workload changes all of a sudden and the write load increases, we allow the hybrid policy to adapt to the workload, meaning that we are going to have the tier level 0 write optimized. So we allow accumulation in the smallest level, in smallest tier, and that makes it write optimized. But given that 90% of the data, about 90% of the data is in the largest level, we allow, we can make the largest level space optimized. That comes with the write amplification cost. So basically, we are, you can see that we accumulate the files, we write exactly like in the tiered policy. But when promoting data from tier 1 into the largest level, we are going to do it like in lambda policy. In a cross-tier compaction, like we are going to compact across levels. It's a space-optimized compaction. So those two levels were compacted together. It's cross-level, cross-year, whatever you call. So the right amplification in all levels, but the largest one is going to be like into the policy. But when doing cross-year compaction, that is doing the space-optimized compaction, the right amplification depends on the size ratio. I expand more on that later, because we can think of right amplification, the amount of bytes, the extra amount of bytes you have to write. If we are compacting 1 gigabyte file with 1 terabyte file, the right amplification is going to be huge. So we want to make sure that we are only going to do this cross-year compaction when the size ratio is good enough, which can be controlled with a tunable, with a table property, a table compaction property. So that's why I say that the hybrid compaction policy is implemented through space amplification Go. You can basically set the space amplification Go, which also correlates with the size ratio. It's a value between 1 and 2. So a value of 1.5 implies cross-year compaction when the second largest level is half the size of the largest level. It helps control the space amplification. So it allows these hybrid layouts where we have a mix between tiered and leveled layout applied to the LSM-tree. So this is how it looks like. This is a benchmark where we show the disk usage for different space amplification Go values. The lower the value, the value you set the parameter, the space amplification Go, the more aggressive the compaction is going to be. It correlates to the size ratio between the largest and the second largest level, meaning that the second largest level is going to be compacted into the largest level when it's half the size of the largest level. So this is a summary on the amplification or on the policies, which one is better. There is the time window, which I didn't cover because we would run out of time. It's a strategy that basically defines a layout where there is like one LSM-tree for each time window. So when you want to read the data from a particular time window, you only need to look at one LSM-tree. It's basically about segregating the LSM-tree into multiple ones where each of one belongs to a different time window. So you can see the summary. We already talked about many use cases where each strategy is good for a particular, where each strategy works the best. So you can look at this summary to figure out which strategy to use. Okay, this is all cool, but we talked about all the strategies, how they work, which files they compact to when, and so on. So I said in the beginning of the talk, what if compaction starts using more disk and CPU than needed? That would cause problems, latency issues, because then compaction would steal resources from the foreground request, like it could be commit log repair and so on. It could be reads and writes from the user through the driver. So it starts bringing problem. But so what happens usually is that the user sets like a static value. The database allows the user to set the amount of bandwidth for compaction statically. So basically, but the main problem with that is that it could end up with endless tuning cycle, because if the workload changes all of a sudden, then the amount of resources you devoted for compaction may not be enough anymore. So the compaction backlog increases and reads start to suffer because compaction is no longer able to keep up with the compaction backlog. We know that in the database we have many internal processes like commit log, repair, and so on. and it's not always clear the amount of resources we need to devote for each one of them. We engineers at ScyllaDB, we figured out that the best way to do this would be to make this self-tuning instead of the static approach. Basically, we want a way to measure the compaction backlog and react to that. So the approach we used is the industrial controller, the PID controller, because we basically wanted to employ a closed loop control system where we are constantly measuring the compaction backlog and normalize the backlog and calculate the amount of resources we should devote to compaction. Because if we use, like I said, if the amount of resources devoted for compaction is not enough, the amount of SSTable files are going to accumulate. So we are going to have read amplification issues, space amplification issues. So nothing better than the database itself figuring out the amount of resources for compaction based on the amount of backlog. We already saw that each compaction policy has its own notion of compaction backlog. So we had to implement like a backlog measuring algorithm for each compaction policy. So we want that the compaction measurement is not disconnected from the compaction strategy goals. So each compaction strategy has its own backlog measurement procedure. So the compaction controller was born. A good example of how it works is if we think of the air conditioner, where the user sets the temperature and its control system of the air conditioner will act based on the sensor data. So that's why it's a feedback control system. We're constantly measuring the backlog and feeding that backlog into the controller, feeding it back. And then we have the actuators in the controller, which is the internal CPU and I/O schedulers. I'm not going to go into details of the schedulers, but ScyllaDB is built upon the C* framework, which was also written by us. It's like an operating system which takes advantage of all the resources made available for Linux, like thread affinity, memory affinity, where we wanted to make it NUMA NUMA affinity. It's basically a share nothing architecture, which is why makes Scylla so performant compared to Cassandra. It's very good. I suggest that you could read about that later. Share nothing architecture provided by C* framework, which is written in C++. Okay, so this is basically how it works. The controller is going to look at the backlog, normalize it, and try to speed up or slow down compaction based on the normalized backlog, which is measured by the sensor, which measures the error, which is the difference between the current state and the desired state. Compaction is basically measuring the backlog, how many bytes it needs to compact to get to the desired state. And given that each policy has its own write amplification, we need to make it per strategy, like I said, we need to implement a method for each compaction strategy for measuring backlog. So this is the method for measuring compaction backlog for tiered policy. It's basically measuring the amount of for a given SSTable file, we are going to subtract the amount of bytes to be compacted. So we would look at the files in the LSM-tree that needs to be compacted, and we are going to see how many tiers it has to travel through to reach the highest tier. So we deduce the amount of bytes already compacted for the SSTable, and the total backlog for this table will be the sum of the backlog for the individual SSTables. So we feed the total backlog into the controller, which will then set the amount of shares, the amount of bandwidth for compaction, and it's closed loop control system because we do that continuously. So the compaction controller in practice, you can see that the throughput of as we reach steady state, you can see that the system behaves very predictable, in a very predictable way. And when the workload, this is a good example which shows that when the workloads changes all of a sudden, then the compaction controller is able to react to that and find the new amount of resources that should be dedicated for compaction. And this shows how we keep the latency, the P99 latency bounded because we are able to not steal resource from the foreground requests. So the controller goals is to make sure that we don't disrupt the workload by compaction, that compaction will only proceed as fast as it should. We are borrowing, we are basically using the theoretical background from the industrial controllers, providing a self-tuning database. We also apply this technique for flushing mem tables into the SS tables, but it's out of scope of the talk. And we can provide a self-tuning database that adapts to the changed workloads without operator intervention. So that's it. I hope you liked it. I will be glad to answer questions if we still have time.
Hi, thank you, Raphael, for your great talk. It seems to me that we don't have time to answer any questions now, but we may discuss any questions that you have in the discussion zone. I think both me and Raphael will be here. Will be there in the discussion in a couple of minutes. So thank you one more time for your great talk, and I think we now proceed to the discussion.
Okay, let's go there. Thank you a lot.
Thank you.